Hi, welcome to me313, Mechanical Engineering Thermodynamics. The topic today is deviations from the ideal cycle, and the section in the textbook is section 10.3. So there's two learning outcomes in this video. First, we want to make sure we understand the differences between an ideal and a real cycle, and then be able to calculate the thermal efficiency of a real cycle. So first, let's go ahead and review the differences between the ideal and the real cycle. And so here we've got a TS diagram. And we'll go ahead and sketch up a four-step Rankine cycle. So we'll start off there with point 1, which would be the outlet of the condenser. The ideal cycle, it's isentropic in the pump, so it goes straight up to a point 2. We enter the boiler up through the saturation region to some superheated point, which would be point 3. That's the outlet of the boiler. And then an isentropic turbine, so it comes straight down to point 4. And then this is all at a constant pressure, the low pressure to connect 4 to 1 in the condenser. So there's the ideal cycle. We have vertical lines here between 1 and 2, 3 and 4, representing the pump and the turbine. And then we have no pressure drops in either the boiler or the condenser. And so line connecting 2 to 3 is an isobar, and line connecting 1 to 4 is an isobar. Now, if we were to look at a real cycle, which has some inefficiencies, and so I'll just go ahead and draw on the same diagram with a different color. First, let's see what happens if we have, for example, an inefficient pump. Well, if we had an inefficient pump, that means that point 1 to 2 would have an increase in entropy, and so point 1 would connect up to about there. So that would be point 2. We call that point 2 actual, and then that point over there would be point 2s. So we're going up to the same initial high pressure that we're doing, but we actually end up having a larger increase in temperature. We're putting extra energy in, and friction is causing that, resulting in thermal energy. Now, if we were to go ahead and look at pressure drop in the boiler, for example, so pressure drop in the boiler, that means instead of following this isobar, if we begin at point 2, we're going to start dropping down to lower pressures, and this is going to drop down and drop down, and maybe at some point out here, and so this would be point 3 instead of over there. Now, if we were to look at the next thing, which would be an inefficient inefficient turbine, this is going to have the same kind of idea in that we're going to start at point 3, and then we're going to go down and to the right, and so there's going to be an increase in entropy, and that would be point 4s, or that would be point 4 actual, and then this is going to end up being at a higher pressure than point 1, and so there would end up being a pressure drop going from 4s to point 1 as we go in that direction. So that's why it comes down to a pressure increase from 1 to 4s going in the reverse direction. And so the area underneath here is going to be less for the same given input, power input, because of these inefficiencies. So the inefficiency in terms of the pumps and turbines we can quantify in thermodynamically, and we're going to look at that in the next example. The pressure drop in the boiler or in the condenser is kind of in the realm of fluid dynamics, which is outside this class, and so we won't really be looking at pressure drops that occur. We should just recognize qualitatively they also reduce efficiency. Okay, so let's just go ahead and do an example. And so this is the example we did in the previous video, where we have steam and it's entering at these conditions here, entering the turbine. That's point 3 right over here. And it's going to condense at 75 kilopascals in the condenser. But what we're going to look now is that we have an 80% efficient turbine. So let's just go ahead and sketch up what that's going to look like. That'll be point 1. We're assuming that the pump is still isentropic, and so point 2 will be straight up from point 1. Then we'll go through the boiler to point 3. None of that changes. But what's going to be different now is point 4 is only 80% efficient, 3 to 4, and so this is going to go over to the right, and there will be 4s. And so if we were to draw an isobar that connects those points right there, there's going to be a point right over here that is straight down that is 4s, and that would be 4 actual. And so point 4s would be the isentropic step, and it would also be at the same pressure there, so we're looking at the same high and low pressure. So let's go ahead and calculate what this new efficiency was, and if you recall, the last efficiency was about 26% when we did this example. And so we'll go ahead and find out how it varies now with this 80% efficient pump. Again, I'm going to go ahead and do this in EES. Let's go ahead and skip over to EES. Here's the example we did in the previous video, and I've made a couple different changes, and so I'm going to go ahead and highlight what those changes are. The changes that happen, I'm going to clear that out of there, is right over here in the turbine, where I have the S3 is the entropy at P3 and T3. Those were given. That didn't change. But what I've done is I no longer have it being isentropic. I'm now finding what the enthalpy is, giving the same two conditions, pressure and temperature, and then I'm finding point 4S using the pressure at 4, that low pressure, and the entropy at S3. So that would be how I find 4S. This is the point that's straight down. And then the next line that I have, point 8 being the 80% efficiency, H3 minus H4 over H3 minus 4S. And so let me kind of write back that equation before we go ahead and solve this to remind you what that is. So what I have is that the efficiency of the turbine is going to end up being H3 minus H4 over H3 minus H4S, right? And so it's that magnitude right there over this magnitude. And I'm sticking 4, which would be the same as 4 actual, just to keep it into the array table. So come back over here to EES, and we go ahead and solve this. And here's our H4S 2402, and we can go ahead and compare that with what H4 actual is, 2545. So see, if it had been isentropic, we would have extracted about another 143 kilojoules per kilogram of energy. We weren't able to do that, and this reduced our efficiency down to about 21%. So come back over here, and so now the efficiency of this cycle is about 21%. So we lost about 5% of thermal efficiency, which is not insignificant. Now, one of the things that we might kind of wonder is, okay, so we looked at an 80% efficient turbine. Now, what happened if the pump is inefficient? So, in fact, let's make it really, really inefficient. Let's go ahead and say that it is only 50% efficient. And how much would that affect the efficiency of this cycle? We saw about 5% on the last one. How much would we reduce here? And while you think about it, let's go ahead and I'm going to go ahead and modify the EES equations to go ahead and do it. So, first of all, to point out where I'm going to modify it here, I've got this isentropic pump. It's no longer going to be isentropic, so I'm going to remove this S2 minus S1 line. I apologize, I'm going to do some typing here. I know it's a little loud. So I'm going to go ahead and get rid of that. And effectively what I'm doing, which I did below it, so you can kind of see, I'm going to determine what the enthalpy is. All right. And then I'm going to go ahead and find out what H2S would be, which is going to be if it was isentropic. And then I'm going to put in the efficiency of 50%. So there's going to be the efficiency. And it's going to be H1 minus H. And this is now going to be 2S. This is a pump, so it's going to be kind of reverse of what we had before. 1 minus H2, right? Okay, so you can kind of tell, since now I've got the isentropic term on the top, because it's going to, the isentropic one would take less work. And so here I've specified what H1 is. This equation gives me H2. So actually, I don't need any of these enthalpies, these duplicate statements. In fact, you might see here, last time I changed it to only 1 to 2, because I'd done 3 and 4. Now I don't need that at all. We can go ahead and delete that. Now, if I didn't make any mistakes, we should go ahead and be able to solve this. And, oops, looks like I got a mistake here. Hold on a second, let me go ahead and find that. Okay, now I see what my mistake was. It was actually when I modified my equation for H2S here. Sorry, that keeps popping up. H2S, you'll see that I actually specified it at P1, but H2S is actually supposed to be at P2. So that should have been P2 right there. Okay, that worked. All right, so then I go ahead and solve it. And so here our efficiency is 0.2071, which is actually not much different than what we had before. I think last time we had 0.208. So it has like 100th of a 100th in terms of the efficiency, or 0.1% in terms of efficiency. Really, really insignificant. So the point of that, if you're kind of wondering why that might be, is if we were to kind of draw this more to scale, that would be 0.1 to 2. But because we're pumping water, and this is incompressible, we really don't put much energy in there. So 0.2 is actually almost right above 0.1. And so if I had a line that goes over to the right, it really doesn't change much. So the consequence is the efficiency of the pump turns out not to matter a whole lot in terms of the efficiency of the cycle, which may or may not be intuitive. So, all right, well, I think that is our last slide for this.